Hello again, everybody, and welcome to another Geo-Institute live stream, the first one of the 2026 Geo-Institute Summer of Live. It's groovy, it's happening, it's swinging, and you found it. To another My name is Brad Keeler. I'm the director of the Geo-Institute, and yes, again, this is the Cross USA Lecture number 1, very innocuously titled for the amazing intellectual growth that you're going to experience during the next hour. If you don't know anything about the Geo-Institute, after you watch this today, head over to geoinstitute.org, and there you're going to find out all kinds of things about us, including that we're a technical society with about 12,000 members, most of whom are geotechnical engineers and or geologists, and that we are part of the American Society of Civil Engineers. And if you like what you see today, and Carlos is going to bring it, so you are going to like it, you should click like, subscribe, and get notifications, and we'll let you know every time we post something to the YouTube channel. What is the Summer of Live, you may ask? Well, we do a lot of live streams, and it's summer, so we decided to call it the Summer of Live, a play on that wonderful 1968 or 1988, depending on your generation, Summer of Love. We have a ton of live streams coming up. They are all free. All you have to do is go to our Eventbrite page and follow the links. It's pretty easy, about 4 clicks, type your name in, your email, and you're there. And you'll be registered for one of the aforementioned live streams. Register for all of them if you like. We would love to have you. The Cross USA Lecture is why we are all here today. And Seth is going to tell you a little bit more about it in a minute. What I'm going to say is this. This is the 16th year that we've had the Cross USA Lecture. It started as a very, very humble attempt to get top-level speakers out into our chapters, places where they wouldn't normally go, and it has turned into, as they say, a whole thing. It used to be 5 lectures a year, and now it's a lot more than that, and maybe you'll find some of that out as we go through Carlos's talk. One of the things that we also are very privileged to have with the Cross USA Lecture is a sponsor. And for the last, I believe, 4 years now, our sponsor has been the fine people at GeoPeer. We have a little message we're going to play from them before we get to today's presentation. Load that up, and you are going to enjoy this for about 35 seconds. About GeoPeer and their work down in the notes below the window where you are watching this video right now. The brand new chair of the local involvement committee is here to be our moderator today. It's the first time he's done this for GI, and he's really, really excited about it, I think. Is that fair to say, Seth?
Yes.
Yeah. All right. Now here to tell you what you're going to see. LICs. I can't get it out. It's Seth. Tell them who you are.
Brad.
Tell them what they're going to see. Yeah. And thanks for being here with us today.
Yeah. Thank you for having me. As Brad mentioned, I'm Seth Stiles. I'm the current local involvement committee chair and a senior geotechnical engineer for Braun Intertech in Kansas City. Today, I will be moderating our Cross USA lecture on fracture rocks. So as Carlos presents, if you have questions, throw them in the chat and we'll discuss them after his presentation. So before I introduce Dr. Santamarina, I want to share a couple of items about the Cross USA series. For those of you who don't know, each year, as Brad mentioned, a lecture is selected. So if you know somebody out there that you think would be a good candidate, You can nominate them at the beginning of each year. Nominations are due in February, so keep that in mind for next year. The Board of Governors then selects a speaker. So the 2026-2027 Cross USA lecturer is Sissy Nicolau from NIST, which is the National Institute of Standards and Technology. And as Brad mentioned, the speaker gives multiple presentations across the country during the lecture year. So if you have a GI chapter that you're looking for a speaker, or a graduate student organization looking for speakers, you can apply now to get financial support from National GI to help the speaker travel to your destination. And even if you don't get sponsorship, I recommend that you still reach out to the speaker if your chapter or GSO can support the speaker, because they have a lot of great information and presentations to share. Specifically here in Kansas City, we had Dr. Santamarina come to our annual conference back in April, and he gave a great presentation. So now I will introduce Carlos. So he is the Clough Professor and Chair at Georgia Tech in Atlanta. Prior to that, he earned his undergraduate degree at the Universidad Nacional de Córdoba, and he completed graduate studies at the University of Maryland and Purdue University. Boiler up. Prior to his position at Georgia Tech, he held faculty positions at NYU-Polytechnic, the University of Waterloo in Canada, and King Abdullah University of Science and Technology in Saudi Arabia. So with that, Dr. Santamarina, if you'd like to share your presentation, we'd love to hear it.
Excellent. Let me make sure that I'm sharing the right one, and could you please confirm?
Yes.
Excellent. Well, Seth, thank you so much. This is wonderful to be here with not only visiting local groups, as I have traveled through the country, but in this case, reaching out to all of you. And so thank you for joining us today and for being here. The title of the presentation is on fractured rocks, and let me start with the following statement. This is an evolving field. Throughout the 20th century, we thought of rocks in the context of rock mechanics. However, as we are moving further into the 21st century, now this is not about mechanics alone, it's about multi-physics rock engineering. And this is readily noticed if you visit the ARMA conference or the journals in our field, and you see that the classical themes used to be laboratorial mechanics, rock mass classification. It was quite empirical, quite deterministic, and it was driven by the infrastructure development, the tunnels, the support, design for the tunnels, slope stability within the mining industry. For example, rock burst has always been a challenging problem, and lots of activity related to petroleum geomechanics, such as fault reactivation or wellbore stability. However, if you see the titles that are beginning to prevail in our journals and our conferences, what we see now is all about multi-physics, fractured rocks, coupled processes, thermo, hydro, chemo, biomechanical, very well extensively instrumented, both laboratory and field implementations. And now more and more we see physics-informed machine learning and AI-assisted engineering. And the drivers are also evolving. There is a lot of influence related to the energy and the energy transition. And for example, we see the carbon capture and storage, compressed air, hydrogen, the whole reuse of existing energy infrastructure and the decommissioning and the deep underground. So it is not that the classical problems are behind us. It is that there are great challenges and opportunities ahead of us. And in this context, I would like to present the following slides, split in three big groups. One is to talk a little bit about intact rock and the formation of rocks. Part 2 will be a little bit on fractured rocks, and part 3 then will merge all these together, exploring properties and processes. As the saying goes, there is a little bit old, there is a lot borrowed, and there is something new, and as we go through this presentation. I will address 3 rocks today, the shales, carbonates, and basalt, and the choice is not arbitrary. It's because of shale gas, most of the remaining oil is in carbonates, and basalt because mafic rocks are all of a sudden regaining some interest in the context of carbon mineralization. But in order to properly work with these rocks, we need to understand where are they coming from, and so shales. And the first thing that comes to our mind when we think of shales is that idea of fissility, the idea of breaking in that blockiness that is not so obvious or easy to understand. And once again, let me remind you that the energy playing field of the energy sector in the US and around the world has been dramatically changed in the last 20, 25 years because of shale gas, whereby from a pad of a well pad like this one, probably there are 10 to 20 or more horizontal wells running sometimes 2, 3, 5 kilometers away from the pad in an amazing deployment. But there are still important questions related to that. And so let's address shales, and shales are very complex because in order to understand shales, we have to start really at the atomic scale, and they're the 0.1 of a nanometer, because that is where molecules, at that scale, molecules, water molecules and ions are interacting with the clay surface, what some of you will recognize from Jim Mitchell's work, and the double layer and that type of phenomena, and osmotic pressures. But then these clay particles really are not working that independently by the time they have been buried for a long time and pressure, and they work in teams forming tectoids. And these are these bunches of clays. There are maybe tens or hundreds of clay layers forming these tectoids, and they bend and they break like when you play with cards. And as we begin coming up in scale, all of a sudden we see the layers and the strata. And if it goes bigger and bigger, now we see the big reservoirs, which may be hundreds of kilometers. So folks, 100 kilometers is 10 to the 5 meters, and we started at 10 to the minus 10, so we have gone through 15 orders of magnitude. This is challenging, and these are shales. I used to think that shales were highly compressed clays, but that was very short-sighted. Actually, shales are a mixture of carbonates, silicates, and clay minerals. And depending on what percentage of clay minerals, clay may be dominant and control all the behavior, but that is not necessarily the case. And when we zoom in and we look at shales, remember that probably they started like a slurry with random orientation, but then after they have settled and they gotten squeezed by the overburden, we see the more rotund particles, the silicates, the carbonates, and precipitates, probably pyrite rhomboids, and this porous sponge, which is the organic matter. This is a shale. 1%, 2%, 3% of organic matter gets trapped in the sedimentation process, and that organic matter is the one that becomes the kerogen and the gas that leads to shale gas. So let's try to understand this better. And so we took UDEC and we represented every particle in UDEC, and these are different combinations in that triangle that I showed you before. So we may want to focus here on the right-hand side. And in this case, you see the organic matter are these darker blobs. You see the tectoids that have bent around. In fact, we have calibrated the program to capture the stiffness of these clay tectoids. And we actually are running measurements here in the laboratory with very thin films to get those properties right. And so what happens is that as the clay sedimented from random orientation in this suspension, and organic matter get trapped and some of the rotan particles as well, the particles become increasingly more aligned with G, with gravity, transverse to gravity. And not only the clay particles become aligned, but the organic matter, which was quite spherical to begin with, now it is soft and viscoplastic, and it gets squeezed and form layers across. This is the origin of fissility. Without this formation process, we would have a mudstone. If we have a shale, it's because this alignment has taken place. And we have huge implications for all our design and working with shales. Now, let's talk about the genesis of carbonates. And first of all, let's recognize that we've been working with carbonates for a long time. The Sphinx is a single chunk of carbonate, and the pyramids, the bulk of the pyramids are all carbonate blocks. And these date from 4,600 years before us. But it was all massive. By the time the Greeks were building the Parthenon, they could make the columns and the beams have to be very thick because they couldn't take much tension. In fact, if you go and observe carefully, many of them are actually exhibiting shear fractures near the support. The deformation failure mode has changed. And that is 2,500 years ago. And then by the time the Romans come about, they learned really how to use the material and geometry together, and they developed the arch leading to the Colosseum and all the beautiful archwork from the Romans. So in this process, we learn the strength of the materials and the properties of the materials. But where does it come from? Somebody said that carbonates are not made, they are born. And why? Because it's all about bioactivity in the shells and the foraminifera, etc., that gets gradually buried. And during burial, the pressure and the chemistry come together. There is pressure dissolution and reprecipitation, and sometimes they form these micrites, carbonates, where there are reprecipitates. This is a carbonate, born, and they are genetically overprinted with these processes during burial. So, not surprisingly, if it started from particles, at very low confinement, it keeps very high porosity, and in fact, it goes to the porosity of an extremely loose sand, like a carbonate sand. Then it gets gradually buried, and they're genetically modified, building up not only stiffness, but also strength. Therefore, these are almost like percolation equations that both stiffness and strength disappear when you go back to a suspension. Now, what happens to the permeability of carbonates? Initially, this was a real cloud of points without discrimination. But then Lucia went and recognized that all carbonates are different. So if you look at carbonates carefully with thin sections or in the microscope, etc., you realize that some of them are made of very small particles, and the fines control the permeability. Some of them appear almost like a sand with no fines, and there are different names the geologists use to characterize these rocks. So if you take porosity and type of carbonate, like fines content for the soil mechanicians, this is totally equivalent to that, you begin to see that you can begin predicting the permeability quite well. Now, if that is the case, now I can combine the porosity or the void ratio in this case, and how much surface is available, the specific surface, to get an idea of what is the mean pore diameter. And now if I plot that data of permeability versus that mean pore radius or pore diameter, the correlation becomes surprisingly robust. This is the formation of carbonates and the development of stiffness, strength, and permeability. Now, I said that the other rock that I wanted to explore with you today and from the genesis are the basalts. 40 years ago, in the 1980s, geochemists recognized that basalts are not as stable as we thought, that under certain conditions, the geochemistry can be quite fast. And then they began doing some calculations starting 25 years ago, and they said, yeah, we may be able to capture the CO2 injected into basalt formations, mafic formations, calcium and magnesium silicates, and this will react relatively fast and convert the CO2 with the dissolved cations into calcium and magnesium carbonates, so we mineralize the carbon. The problem is, and that the most beautiful example is Carfix. There is also a project in the US. Carfix has done it very successfully in Iceland. The issue is, what is the aperture of these fractures and what is the porosity of the rocks? The fractures are always responsible for the highways of transport, and the porosity in the rock is all about storativity and then reactivity. And so we went back to look into these formations, and we have visited a large number of basaltic formations, and this is more or less a summary from the literature and our own experience. We have a magma chamber, and the magma has lots of dissolved gas. So as it begins coming out, it gets depressurized, bubbles come out, nucleate, gas comes out of solution, nucleates forming bubbles, like when you open a Coca-Cola bottle. And then these bubbles begin growing, and sometimes they coalesce, and sometimes they expand so much it's an explosive eruption, or sometimes it just flows out, forming lava fields. Those lava fields eventually cool then relatively fast for crystal growth, and so it forms these basaltic formations. And if the cooling is slow, then it develops a contraction pattern similar to desiccation cracks, but now it's because of thermal contraction, and they begin splitting, forming these columnar shapes. Now, if what I said is true, then these are different field case histories that we have analyzed to get the statistics of block size and the statistics of fracture aperture. The fracture aperture must reflect the thermal contraction of the block. So they must be related, and indeed that is the case. The contraction factor, alpha, the thermal contraction coefficient, is affected by mineralogy, but this is very predictive. And this is very important because this is the space where fluid will take place and mineralization, volume expansive carbonation will occur. Now, when we look into permeability of the matrix, now we have to see how did these bubbles coalesce and merge. And sometimes you look at thin sections, or you look with a microscope and you see that they coalesced, but there was already quite viscous. So you see actually the two bubbles are still preserving their shape and sometimes creating contiguous pathways for flow. So clearly then, as the porosity increases, the probability of having contiguous passes for transport increases, and so does the permeability. Of course, we're here in what, 7 or 8 orders of magnitude, but there is a change in the pore topology as we move into lower and lower porosity and lower permeabilities. When we combine all the data available now, we can do something very neat. We can actually simulate in 3D the coalescence between bubbles, and depending the amount of bubbles and the porosity, there will eventually generate more and more conductive pathways. And then we use Navier-Stokes to see the permeability of the basalt. In the background here, all the gray points are unclassified. We really don't have more information about the type of formation. But then we have pumice and we have the basalts, and this is our digital rocks following the methodology I just prescribed, giving us great insight into the evolution of porosity in the matrix of basalt, and from the previous part, the aperture, the evolution of transmissivity in the fractures between the basalt columns. Now, in the next section, let me say something about fractures. And as soon as we hear fracture and fracture rock masses, of course, we think of rock mass classification. And I think that this is one of those points that is in a major transition phase. Look, it has served us very well. Bienasky's methods and Nick Barton's and NGI team, the Q method and other methods from Everhook, and then relating to rock strength. But some of these, well, this is a schematic or a chart. This one is a multiplicative factorial format. This is additive. And these are all different dimensions, totally independent. So it really makes no mathematical sense. So from a measurement point of view, measurement theory, we are violating measurement axioms. But I think that something as insightful as they are, I think that there is something very important now. Throughout the insight of all these studies, now we recognize what are the most important parameters that govern the rock mass behavior. And now we're going to begin placing this into large data sets, and yes, using the power of machine learning to discover that manifold in the n-dimensional space where the rock mass exists in order to predict its behavior. This is where we are today. But let's go back to fractures, and we always start, if you look at the classical books or the National Academy of Engineering, two compendiums of fracture rocks, we go back to mechanics, mode 1, mode 2, mode 3, and we see that in conjugate fractures at multiple scales is telling us where the sigma 1 is, and probably an idea of the friction angle being the tension of 45 plus or minus V/2 in the more Coulomb formulation. And we can even extend these ideas quite nicely. For example, if there was a lava riding over a sandstone and all of a sudden vaporizing the water so fast that it produced a hydrothermal fracture and this plumose shape, you see how the fracture evolved. Still mode 1. The story gets more complex, for example, when we have massive foldings, and of course it is satisfying mechanics, but now there is a rotation of principal stresses and relative stiffness between layers, trying to break a multi-layer set of Oreo cookies with the soft and the rigid, etc. How would the fracture pattern form, and where would it break in tension and where would it break in shear? But furthermore, let's go back to shales. When we go and fracture a shale, we do fracking, hydraulic fracture, how will it fracture when it is fissile and it has this pre-structured nature? So we explore that. And in fact, we were inspired by a visit to Machu Picchu. When you see here the settlement of the end of the foundation, you see that the distortion propagated upwards. By the way, notice the size of people. These are huge blocks. And there is distortion, and this dilational distortion actually leaves lots of gaps, which is going to dramatically increase hydraulic conductivity beyond where the fracture is. Let me show this in a more demonstrative way. This is a set of a block, and when you push, you form the wind fracture, but follow what is happening at the center. All the fissile positions, or these are pre-existing fractures, begin opening up, and this produces really, first of all, a very diffusive acoustic emissions. If you were listening carefully, it's not a nicely defining a penny-shaped fracture, but furthermore, it's creating lots of a network of passages for gas recovery. We tested this. This was the beginning of a large scale true triaxial. It's 0.5 meter by 0.5 meter by 0.5 meter with 6 bladders to control sigma 1, sigma 2, and sigma 3. And then we inject at the center a thick caulking fluid. But we have to assemble the fracture rock mass. And so we did it with different topographies, different fabric arrangements. In any case, let me show you one result. This is by the time you pull out very carefully and you recover all the invasions of the cocky and silicone, this is the imprint of the fracture. It's far away from a penny-shaped fracture, and it's invading sometimes along corners and between blocks, and along the dilated plates of blocks, between blocks, is invading all those, which is wonderful in order to recover shale gas. So now I'm ready to talk about some of the properties and processes that we may encounter as we move further and further into this multi-physics rock engineering that our field is migrating towards. So we already said that fractures form the geoplumbing of the formation in most cases. There could be rare cases that excessive shear has formed so much gauge material that are actually aquithards, but in most cases, fractures are the geoplumbing of the formation. And the key here is that fracture transmissivity scales with the cube of the aperture. That means if we have a set of fractures, parallel fractures, and they have an aperture distribution, and they will, nothing is identical, so there will be a mean value, but some of them will be narrower, some of them will be wider, typically with a coefficient of variation of about 0.5. And then we use that rule to see how much is each fracture transmitting, and I add them up and I see how many fractures are responsible for 90% of the flow. You end up that 1% of the fractures carry 90% of the flow in most cases. This may have some advantages. If you need to plug, you have fewer ones to plug, but it has many disadvantages because this flow focusing along the more transmissive fractures means that water will migrate through that fracture, depleting temperature nearby that only fracture. So it may deplete the reservoir, what you think is the reservoir, much faster than you think, hindering the long-term production from geothermal reservoirs. So how are we going to homogenize transmissivity? The other possibility that may happen is that that fracture that carries most of the fluid carries most of the reactants. For example, acidified water. And as it acidifies the fracture becomes dissolved and it becomes wider. The wider it becomes, the more fluid it carries, the more dissolution, and there is a feedback loop which exacerbates short-circuiting. So we have to be very careful with this. This is an inherent property of fracture rock masses. Now, in order to understand how the fractures are going to interact, we have to recover a fracture and study the surface topography. And you can do a Fourier analysis of this topography, like if it was a summation of sinusoids, and you do the power spectral density, and you conclude that, and I should have put here, there are a large number of references, original, we just added a few to this plot, I apologize, but it is in our publications in a complete form, but you will realize that this is problematic because this is called fractal scaling. And that means that if you test a 10 by 10 fracture, or a 1 meter by 1 meter, or a 1 kilometer by 1 kilometer, you're going to have different properties. So upscaling becomes a nightmare. Now, when fractures form, let's say that it's mode 1, so it breaks in tension, so the right hand and the left hand of the fracture are perfectly mated. And so transmissivity is going to be very low, and basically the aperture is going to be very, very low. But that's the reason why we need to put propants when we do hydraulic fracturing to make sure that they remain open. Now, if the fractures, in addition, experience shear, now it's like knuckles on your hand. When you move them, at this point they are mated. When you move them in shear, you see how the aperture increases because of dilation, overriding of the asperities. There is some shear of asperities as well, and that gives rise to an aperture field, which, by the way, is inherently anisotropic, transverse to the shear direction. So to study that, we did this ring shear device where we can control the normal stress and apply torsion. And in summary, this is the fracture. let me conclude here by saying that the transmissivity, as you can imagine, decreases as we increase the normal stress, and the transmissivity increases as we increase the shear displacement. Having this type of fitted constitutive equations is critical in order for upscaling and for our numerical modeling abilities. In soil mechanics, we have talked a lot about unsaturated soil behavior with huge accomplishments. We don't speak so much in that wording in the rock mechanics field, even though oil recovery is all about mixed fluid flow. By the way, the emphasis in rocks is about flow. The emphasis in rock mechanics is about effective stress, let's say something along the lines of Bishop with its limitations. So here the emphasis is on flow, but it goes back to the same physics: interfacial tension, contact angle, and pore connectivity and topology. So now we can also measure the soil water characteristic curve for a rock. In other words, the water content versus suction for a rock, and determine, for example, the air entry value. Now we can relate the air entry value to the largest pores in the system, because the air will, if it is a water saturated rock, air will enter into the largest pore first. But the air entry value that we pick up from these saturation capillary curves really correlates best with the 85th percentile of the pore size distribution. And these are for different rocks. And this air entry value is very important because that is the maximum pressure that is exerted isotropically around the whole block. After that, air invades and suction is patchy, is in regions, both in soils and rocks. But that is the point where that equivalent isotropic confinement is exerted throughout the whole phase. And now we may wonder, how much will the rock expand if we remove that suction? We tend to think that rocks are infinitely stiff, but they are not. And so this is the case in point. When you take a rock and it is fully saturated, and you begin here you're saturating it, and then you dry it, it does experience quite measurable strain. And of course, the strain will be higher if the rock is soft, low stiffness, and if the rock has very small pores to mobilize high suction. But it's measurable even in some granites and marbles and limestones. This will have implications, for example, for the ability to seal around wells for decommissioning or formations in order to store gases. So now we go back to this idea that fractures are the geoplumbing. You see, along the fractures is where the fluid is going to flow primarily. But if we do the suction saturation curve, this is for a fracture. We also measure that one for a fracture. And this is for the rock matrix. This is the combined for the fractured rock. And you is clearly seen that most of the storage is taking place in the matrix, while flow is in the fractures. That is the interplay between the matrix and the fractures. Now let me jump into another phenomenon that is gaining great relevance, and it's along these lines of multiphysics, thermo-hydro-chemo-biomechanical coupling. Here I'm going to talk about hydrochemical coupling. And two phenomena are always intimately related. Is the two sides of a coin: dissolution, precipitation. And they will coexist, not in a space. They will be displaced in a space, but in time. In other words, for example, inject an acid front, you will begin dissolving, but at some point, most likely, you will end up precipitating. So how does that happen? By the way, before I leave this slide, these are two beautiful examples. These are called stalolites, and you'll find them in every carbonate, in every tile in the bathroom or and floors. These are all evidence of dissolution. what remains is the insoluble particles. And these are Liesegang bands where the fluid that was going along the fractures now diffuses and reprecipitates in the matrix in a banded form called Liesegang bands. These are phenomena that are going to coexist in carbon capture and storage. I will not go into details, but they're critically important here. And as I said before, in some places there will be dissolution. So this is a three-dimensional plot, which is how fast it dissolves, how fast it moves through, and how fast it diffuses, controls the phenomenon, but easy to recognize. If the fluid flows very fast compared to the rate of the solution, the fluid will reach far distance and continue dissolving the fracture, so dissolving the fracture in more or less homogeneous way. However, if the fluid, so this is the opposite case, if the fluid dissolves very fast the rock, imagine that you're trying to inject water very slowly into a bucket full of table salt, so it will dissolve mostly at the entry and less further out by the time the fluid has already become saturated. So the form, the rate of invasion, the rate of dissolution become very important for the pattern of dissolution. On the other end, there will be precipitation, and it reminds us of frozen ground or the effect of salt precipitation and concrete durability. They are all exactly the same processes. The precipitating crystals begin to grow. In order to go through another pore, they have to go through, and then they have like capillary pressure squeezing them, and so they can do two things. Either they invade the next pore or they push grains out and they fracture the rock. Recently, my colleague here, Hain Huang, has really decoded and captured in mathematical form how this takes place during carbon mineralization in rocks. The other component of the coexisting physical processes are thermal processes. And now, how does temperature propagate through a rock? Because temperature is random vibration, right? But these are not so crazy. They are correlated because they are attached, atoms are attached to each other. So they vibrate in some synchronicity, which is the vibration that you see in that lattice here on the screen. So with that in mind now, imagine that I have a fractured rock mass. These are different rock slabs stacked together. We drill a very small hole and we put a thermocouple above and below each fracture. In this system, we apply a load, we put a hot plate at the top, a cold plate at the bottom, we measure the thermal conductivity. And at equilibrium, something rarely observable emerges, that within each rock mass, heat conducts very effectively. But then it gets kind of stuck at the interface because of thermal contact impedance. And then there are these jumps in temperature. Now, how can I reduce the thermal contact impedance? Two simple ways. One is I squeeze the rock more. The other one, I put fluids inside. This is the same as trying to grab a very hot pot. You don't squeeze it with your fingers, and you might as well use a cloth, but a dry cloth, not a wet cloth. The same two concepts, confinement and moisture, and this is what the data is showing. I increase confinement, I increase the conductivity of dry rocks, but I increase saturation, and I produce a very high increase in the conductivity of fractured rock masses. In the context of soils, and I keep doing the contradiction here because it's very nice to learn from one and the other. In the context of soils, we recognize that repetitive loads were very important, mechanical, thermal, chemical. In fractures, they are not so sensitive, particularly not sensitive to chemical cycles like it could be for a clay. But thermal cycles are not scale dependent. So they are as important in a sand as they are going to be in a massive rock mass. Case in point, this is the Masada monument in Israel, and some of these walls are falling down, and this was a study done by Stephen Glaser and collaborators, and they put extensometers, and they couldn't find any correlation with rain, that's in the next to the Dead Sea, it doesn't rain, or with seismic excitation. So we were looking at it, and we noticed these choke blocks that fall behind. And I think that this is the mechanism that is at the heart of how these walls are falling. And we see this wedging its way into this system, and this is beginning to tilt. This is not toppling. This is not the Goodman's toppling mechanism. This is thermal ratcheting. And I think that the same is going to happen below the Grand Canyon skywalk with some of these wedges. So what is the procedure? When it is hot, the rock expands free in the direction of the free space, and including plastic shear displacement at the base. When it gets cold, it contracts because this friction traps that displacement. It contracts on the back, and the choke blocks fall further down, expands to the right, contracts, the choke block fall, and this is beginning to walk, to ratchet, thermomechanical ratcheting its way out. And yes, you can mechanically describe it, mathematically describe it, experimentally demonstrate it in the laboratory, etc. So in the last couple of sections, I will address other topics that are emerging. One is that we're getting deeper and hotter. In fact, how hot? Super hot. Super hot meaning that we want to begin operating at temperatures that exceed 22 megapascals. This is equivalent to 2,200 meters of water in a water column. So this is pretty deep, and 374 degrees Celsius. Beyond that point, water is very weird. There is no more liquid to vapor phase transformation. Water begins dissolving organic matter and stops dissolving in sodium chloride. Sodium chloride precipitates. Very weird. And that would be a wonderful space to begin pulling geothermal energy, because 99% of the Earth is hotter than 1,000 degrees Celsius. So it's a wonderful opportunity. The problem is, how do we get there? And so we began looking at how rocks are going to behave. This is just a snapshot of the large database that we have put together. But just to give you some physical intuition, stiffness decreases with temperature. Of course, by the time it melts, there is no more shear stiffness, let's say. Stiffness increases a little bit with confinement, and stiffness decreases with porosity, as we had noticed before. These are for granite, sandstone, basalt. Now, if we look at the strength of granite, also decreases with temperature, increases more sensitively with confinement, like a more Coulomb and Hook and Bray, and the peak strength decreases with porosity. Now, we have a large database on this, and it allows us to explore other things. For example, the brittle to ductile transition of these rocks because if they are not brittle anymore and they are ductile, and you try to do a hydraulic fracture to create pathways for fluid transport to recover the heat, then if it is ductile, it will just inflate like a balloon rather than breaking into a fracture. And now this n-dimensional space of all the variables, machine learning allows us to, once again, identify this manifold in this n-dimensional space that we cannot even conceive. But as the data begins to predict, confinement is important, temperature is important, porosity, if you have a shale, clay content, and if you have granite, biotite. Very informative, in addition to being very predictive. Finally, to conclude, let me say something about modeling, because, as I said earlier, we may not be able to do the experiments that we need to do because of scales and the huge forces that are required. So we will have to do some experiments for whatever we can test and then upscale with numerical experiments. I used to think that that was an oxymoron, but this is a true reality. That's what we need to do. And just to remind you that we have to go back and think in terms of scales. If we have a tunnel in the middle of a perfect rock mass with no fractures, then here's solution. Theory of elasticity, elastoplasticity will work fine. But if the fracture spacing, it becomes relevant with respect to the diameter of the tunnel or the size of your footing, etc., you have to begin looking at the blocks themselves, and that is Dick Goodman's block theory and sheet. If we have more fractures, that becomes more difficult, but it's not an equivalent continuum because it still has the prevalence of the fractures. So we need to implicitly capture fracture effects into continuum. These are called implicit joint continuum models. Finally, if it is massively fractured, then we have like a soil. Then we go back to an equivalent continuum and some clay. And this is what this slide is trying to capture. In closing, this is an evolving field, actively evolving. We have to start by assuming that all fractures, all formations are fractures, and recognizing that fractures govern all properties, from the geoplumbing and in the fractures to the storativity in the matrix, and these two are interacting in all physical dimensions. That we need to combine, we don't have an alternative, physical experiments with numerical experiments in order to do the upscaling. This is all about multiphysics. This is where the richness of the next phase is, and we are getting into deeper and hotter formations. We will require proper experimental methods and simulators, and now we are also in the presence of these major avenues converging: a revolution in sensors, availability of data, physical understanding, simulations, and machine learning. We're moving into a space of AI-assisted engineering. This has been a massive effort, and lots of people in different realizations of the group, and I am not quite sure that I must be forgetting some of the most active contributors to the presentation. To all of them, my gratitude and their merit. Brad, you are an amazing dynamo to the Geo-Institute and to all of us and your team. And so to the Geo-Institute yourself, and Seth, thank you so much, and to all of you in the audience. Thank you.
Dr. Santamarina, thank you so much for that presentation. For those that are watching, make sure to submit your questions to the chat, and we'll work to get through as many as we can here. I wanted to start with a question. Maybe this is kind of the big one. You mentioned machine learning, and I think about all this data that we can collect. So maybe specifically if we're thinking about a tunnel or a rock face wall, like a cut along a highway or something, we can collect all of this data. I anticipate machine learning tools will become more involved in design and helping engineers make decisions. So what opportunities and concerns should researchers and practitioners keep in mind when looking to leverage machine learning?
Okay, I think that this is already happening. We are starting similar to Peck's observational method. We are starting now with imagining a reality based on the few boreholes that we may have along the way, whether it's soils or fractured rocks or misfaced conditions. And we are going to begin updating the model as more information becomes available. But we're going to have a digital twin of this whole configuration, including some statistical realization of possible rock mass configurations ahead of the tunnel. One of the problems we have, and of course all that has to be trained, so we will have to have the forward simulations to train the system because we don't have enough physical realizations. This is not like Google that has data from our cell phone going all around the highways. How many tunnels do we have detailed data from? So we will have to do some forward simulation to train the system to begin with. But I would like to mention one caveat that you were referring to. For example, we are training algorithms to predict properties. Imagine, for example, the stiffness of rocks. And we face that problem in some of the cases that I show, so I would like to highlight it. The easiest way to measure the deformation of a rock is platen to platen. But that captures all the deformation of the sitting effects of the rock, which is huge on the measurement of the stiffness. So we need to measure the stiffness with the strain gauges. But that's a pain because you need to get the cables out of the membrane. And so much of the data that is available is systematically biased. And now we may risk systematically, if we don't curate the data properly, we are going to create a bias in the trained algorithms. So this is not just, let's collect the data, dump it, and let the system react. We still need to remain very thoughtful about it.
So I have a follow-up question. I'm curious if you have any thoughts on supervised versus unsupervised learning. So like supervised, telling it what parameters are correlated based on our previous understanding of rock mechanics, for example, versus unsupervised, just saying, here's data, find connections, and it may find a relationship even though there may not be a known correlation between parameters. Your thoughts on that?
We have done this now for 4 or 5 different cases, from soils to fractured rocks. And at this point, the way we are doing it is we are progressing very slowly. And there are 2 reasons for that, Seth. On the one hand, we want to make sure that we are doing the right things and we don't over-parameterize the system and overfitting, etc. So we have reliable predictions. But the other thing is we still want to learn. We want the machine learning, like I did, for example, in the brittle to ductile transition in super hot conditions, trying to identify what is governing the process. So there are 2 reasons why we're going slow. One is for confidence. The other one is to build the physics into it, but also because we want to use it to continue learning and extracting important information for our field.
Okay. So we'll go to some of the questions from viewers. I find this interesting. So regarding the ratcheting mechanism, is there like a reliable way or a way to estimate time to failure for the thermal ratcheting? Is it predictable, I guess, or do we just know that it's occurring and there will be a future failure?
Very good. Okay. So thermal ratcheting, by the way, it will appear in many cases. One is on exposed slopes, like the one I showed, but it will also happen, for example, inside reservoirs where when we compress air, we increase the temperature. When we pull it out in compressed air energy storage, we cool it, and that with cycles, that is also thermal ratcheting. And so when you do the analytical simulations or numerical simulations, you realize that in order to actually happen, the heat has to have time to enter the rock. During a daily cycle, that heat only affects the skin of a big block, and that skin doesn't deform enough to overcome the displacement for friction mobilization. And so in all the blocks that we have analyzed, thermal ratcheting is happening with seasonal thermal cycles and not with daily thermal cycles. The shorter answer then is yes, it can be modeled, it can be analyzed, and it will remind you something like pile-soil interaction. This has a similar flavor of mechanics behind it.
Okay. We have a question here about unsaturated flow in rocks. So in the context of land subsidence, do do you think the coupled flow mechanical behavior of fractured rocks is becoming an area of research interest?
Whoever is asking the question has some particular case in mind. When we think of land subsidence, for example, I think of LA during oil production. I think of a Maracaibo Lake, Lagunilla area, because of oil production causing subsidence. Or water production, Mexico City and around Pisa Tower, etc. In most of those cases, it's really unconsolidated sediments, or it happens in unconsolidated sediments. So I don't have a case in mind where pressure cycles cause subsidence in fractured rock masses. That being said, one of the problems in oil production is fault reactivation. So you change the pore pressure, you reactivate pre-existing faults, which is a problem now because you have an active pathway for leakage and also it shears wells, etc. So clearly, pore pressure cycles, even in oil production, in fractured rock masses, could lead to ratcheting. However, when we think of subsidence, typically the cases in mind typically involve uncemented sediments.
Okay. For those watching, continue to keep submitting your questions, and we'll get as many answered as we can here. Carlos, one thing I want to talk about. You talked about brittle to ductile transition becoming important or being important. How does that response, brittle to ductile, impact or influence the behavior and impact engineering performance?
Yes. So based on all the data that we have collected and with pressure and temperature, etc., for most rocks, we are not going to see the issues of brittle to ductile transition in the near surface of infrastructure projects. So we have to begin thinking in deeper formations. But if you are into earthquake engineering, that is where the upper layer goes into the aseismic region, because you have gone beyond the brittle to ductile. So in the ductile, it just keeps creeping rather than creating a stick slip deformation. So it's very important for earthquake engineering. And now, it still is interesting, how does a rock go from being brittle to being ductile? And so imagine that you can do the following situation, and it was done by Dr. Adrian Garcia. You assemble a rock like with DM, with elements, and you cement it in such a way that it gives you the same behavior as a set of triaxial tests. And then you analyze how is that, and with the same set of parameters. The only thing that you change is the confinement. And then you begin exploring how did the rock break at the beginning at low confinement brittle and at large confinement in ductile. And it's all about a prevalence of tensile failures in the brittle regime and shear failure in the ductile regime. So what is really happening is a dramatic change in the evolution of the rock, intact rock failure that is taking place.
You know, I was thinking, we're talking about deep materials, and so to drill a boring, it's quite the undertaking. It's I imagine quite expensive. Are there geophysical methods or other exploration methods that are cost effective or allow for evaluating larger data sets?
Very good. Imagine trying to drill for one of these super hot reservoirs that you have to drill into several 4 or 5 or more kilometers deep. 350, 400 degrees Celsius. Imagine the effect on the drill bit. Imagine first of all, the tripping, bringing the drilling bit up and down, the time it takes, and then trying to put a casing and doing the cementation, the cement job. What cement works well at 380 degrees Celsius, and we don't have electronics to handle that heat. Electronics get cooked. All our standard electronics at 70, 80 degrees, 150, they are all cooked. And so huge challenges. I don't underestimate the challenges ahead of us. But then the alternative is to explore remotely with geophysics. And we do lots of geophysics also in the near surface. And a couple of caveats here. In the laboratory, we put piece of crystals in the triaxial test and we measure acoustic waves. Those are probably working in the megahertz, about megahertz, 500 kilohertz and above. Because the wavelength has to be shorter, much shorter than the specimen. Now, if you use high frequency in the field, the wave is going to go and bounce at fractures. Part of the energy is transmitted by its ballistic propagation. If you really need to understand the rock mass, your wavelength has to be much longer than the fracture spacing. And by then, it behaves almost like a soil. The wave velocity is determined by the state of stress with all the anisotropies, etc. So geophysics is wonderful in this context, but the interpretation of geophysics has to be very carefully conducted.
Yeah, I think it's always good to tie the mapping back to actual exploration locations. We have another question here from the audience. So specifically looking at dam foundations and talking about grouting and seepage reduction within fractured rock. So can you talk about the importance and the concepts that you discussed today being applied to seepage reduction?
That's a huge problem, and if you are in a carbonate terrain, then that allowing for any seepage is only aggravating the problem. So that's something that has to be handled rapidly. I also remind you that Teton Dam, when they excavated in the forensic study, even though they have done the most expensive grouting curtains possible, a person could walk through some of the fractures that never got a pound of grout. And so grouting is a very tough science. It's a science and an art. So in particular to your question, now there are different types of grouts with different viscosities. And there are also chemical grouts depending on how narrow the fractures are becoming. So it's not just Portland cement grouts, but also chemical grouts. And now we are exploring the possibility of injecting two fluids that they are stable until they find each other, and at that point they precipitate. So precipitation reactions, and is working quite interestingly.
All right. Well, that concludes our questions from your presentation. So again, I thank you for taking the time to share with us today, and I look forward to your second and third lectures later this summer.
So thank you so much, and to all of you.
That was fantastic. Thanks, Seth, for your moderation skills today, and Carlos for getting our summer season kicked off right with a lecture. When we were talking before we went live, and I talked about columnar basalt in Shenandoah National Park, I had no idea it was going to make a guest appearance here. And that, I don't know, because I don't remember. I just saw it. Did you mention where that formation was that you featured in that slide?
That one was Iceland.
Okay. Because
It's amazing.
it's fascinating to see that way. The one in Shenandoah, a lot of it's covered by vegetation. So you can see the underside of it, but you don't see that really dramatic top like that. So that was really cool. Fantastic talk. Really appreciate it. For all of our viewers that ask questions, thanks so much. That's what makes these live streams so vibrant and exciting. And if you want to pass this on to your friends, that link will stay the same that you watched this at forever and ever and ever, or at least until someone evil takes over Google and runs it into the ground and YouTube doesn't exist anymore. Then we'll have to figure out some kind of plan. But for now, you can keep watching it where you see it. Our next live stream will be 1 week from today, next Tuesday, June 2nd. You can come right back here to hear from our friends at Tab Logs. And they are going to present, I had the whole title up here, and then I put it away, and bad for me, right? Democratizing software for geotechs. You're going to get to hear from Tab Logs founder Declan Vanderhoorn next Tuesday. Just another amazing part of the summer of live. Carlos, thank you so much for doing this today. Thanks for all the cross USA lectures throughout the year, and we really do look forward to the other 2 live ones.
Thank you so much to all of you.
And thanks again, Seth, for moderation. Our producer today was Aurora Flieger. We will see everybody soon with another Geo-Institute live stream.